And so the first thing we're going to talk about is resistive circuits. So now we're at the start of talking about robotics. And we're going to talk about electric potential, voltage, current, and resistance. And then how to wire these things up in our class, and we'll get to some hands-on circuits next time. But I just want to talk first a little bit about how to think about these things, like how to have intuition about what's going to happen, and then some calculations. The first thing you have to know is that current, electric current, is what powers devices. Um, and electric current comes from the motion of electrons. Voltage, though, is so voltage doesn't directly power devices, but it is what makes current flow. And in order to understand the relationships between these things, between these electronic quantities, these electric quantities, it's helpful to think of an analogy with fluid flowing through pipes. Okay, so here's what we're going to think of. We're going to think of a setup like this. Where you have a pressure P1 here, and a pressure P2 here. And you have a fluid filling part of this connecting tube. Okay, this is a liquid. And we're measuring, so let's say this is the point where we're taking the measurement. We're measuring the rate of mass flow past this plane, this part of the pipe. Past this point. Okay, so if the fluid is flowing really fast this way, then this is going to be a big value in this direction. If it's flowing this way, it's going to be a big value in this direction. Okay, so that sort of makes sense. And so how would you make the fluid flow? Well, you can only do it so it wouldn't take very long before this thing would stop working. But if you're measuring it as you change these pressures, if you have a high pressure P1, you're going to much higher than P2, you're going to get flow that way. And if the pressure P2 is much higher than P1, you're going to get flow that way. So if P1 is greater than P2, you're going to get flow in this direction. And if P2 is greater than P1, you're going to get fluid flow this direction. Okay, so notice that those individual pressures are things you can measure. But what really matters isn't either one of those individual pressures. What really matters is the difference between the pressures on the two sides. Okay, so what really matters for the fluid flow for the flow rate is the difference between those pressures. Okay, so like look at this thing. If we made this pressure super high, that doesn't necessarily mean fluid's going to go that way, because if this is just as high or higher, fluid won't go. If these two are exactly the same, even if they're really high pressures, that liquid's just going to sit there in the middle. Okay, if this is really high but this is higher, fluid's still going to go back this way. Okay, so remember, this is going to be important. The individual pressures, like you could measure that, you could put gauges up to them and measure that. But if all you care about is how this fluid's going to flow, what you really care about is the difference between those pressures. Okay. I also want you to notice for a given pressure difference, the rate of mass flow, the rate of flow, is affected by how thick that pipe is. Okay, so if you have something like this, and let's say the pressures here, I'm just going to make up some some pressure. So let's say that's 1 bar of pressure there and half a bar of pressure here. Okay, you're going to get a high flow rate compared to a thing where you have 1 bar of pressure on this side and it's going through a very narrow passage. It's still going to go this way, but that change in thickness is going to affect how much mass flows through that point. Yep.
Even if the right side is half a bar, same as
Yeah, I'm sorry. Sometimes when I try to talk and write, it doesn't go well. Yes, that would have been very confusing in everyone's notes later. So this would be a low flow rate. Okay, so anybody have any questions about this setup? All that stuff makes pretty good physical sense, I think. So now we're going to think about each one of these things in terms of electrical quantities. So here's the analogy. Electric potential is the equivalent of the pressure at one end, at an end. The SI units for electric potential are volts. And if the electric potential is the same at both ends of a wire, okay, well, if electric potential works like pressure, you would think that the electric potential being the same at both ends of a wire would mean that no electricity flowed, no matter what that electric potential was. Are you with me on that? And that's the way it works. So no electricity flows between the two ends. Voltage. So let me say one more thing about electric potential. So electric potential is something you could measure at a single point, okay? At one point. Okay, so this is related to voltage. Voltage is the difference between the electric potentials at 2 points. So for example, if you have if the electric potentials at two ends of a wire are the same, then the voltage between those ends is zero. Okay, even if the electric potentials are really high. So the voltage is just measuring the difference in electric potentials. Okay. The SI units for voltage, as you would imagine, are volts again. And that makes sense if you think about the fact that voltage is just subtracting two electric potentials that have units of volts. If you subtract two things with the same units, you get those units again. So electric potential, I said, is something you could measure at one point. For voltage, you always need to be taking that between 2 points. Okay. So the voltage is always measured between 2 points. Okay, so electric potential is like pressure. Voltage is like a pressure difference. Yes?
Would the electric potential be like the 1 bar that you
Yes,
stated?
exactly. So like in this example, this is like the electric potential is 1 bar here. The electric potential here is half a bar. The voltage between those would be 1 minus point. So the voltage would be 0.5 bar with the higher side here and the lower side here.
My question
Yeah.
is, you said that electric potential can be like has to be measured at 1 point.
Yeah.
Can you measure it at a point within the flow, or is it only measured at the
for our purposes, we're only going to, so we're going to think of like the U-shaped part as like an electric device. Okay. And we're not going to measure the electric potential inside the device. We're only going to measure it at the side. So like basically like if you think of an electric circuit, we're going to think of the so there are devices here, here, here. We're going to think of the electric potential at the wires that connect those things, not on the devices themselves. Okay, so electric potential and voltage are the things that sort of force electricity to happen. The electricity, though, the thing that powers devices, is the current. So that's the next thing I'm going to talk about. And current is analogous to the rate of water flow. Liquid flow. And the current is always going to flow from the higher electric potential toward the lower electric potential. The SI units for current are amps. Amperes really, but people just say amps, and you use a capital A to represent it. An amp is a big amount of current. So the currents that we're going to see in our electronics are going to be milliamps, thousandths of an amp. Okay. And one thing I want you to notice about the current, yes.
What does SI unit mean?
Oh, that's like I think of it as standard international. It really is French, but it's the international units. It's the type of units that people use in every country except the U.S. basically, but we're going to use it. But it's meters, kilograms, and then for electricity, it's these. And notice that current has a magnitude and a direction. So in most electronics, it's not enough to just know how much electricity is flowing to know the magnitude of the current. You also need to know which direction it's flowing. And, so like if this is your analogy, in this case, water would be flowing from the left to the right. Okay. And we're going to think about it the same way with electricity. Okay. But we need to always be aware which direction it's flowing. And then the last one, so electric potential and voltage make this stuff happen. The current is what really matters for powering devices. The last thing we need to talk about today is resistance. And this is analogous to the narrowness of the pipe. I mean, so that's a little awkward, but the resistance goes up as the pipe gets more narrow, The SI units for resistance are called ohms, and you use the capital Greek omega to represent an ohm. So if you increase the resistance of a device, then the effect is that the current is reduced. And if you decrease the resistance of a device, the effect is that the current is increased. Yes.
Can you give an example of high resistance versus low resistance in electronics?
Well, that cabinet over there has a bunch of little drawers, and each of those just has resistors in them. And so for us, really, like the resistance is just like we'll just go to that and say you want higher resistance, go grab a bigger number. But the way resistance, so just kind of like a pipe, like if you have electricity flowing through a fatter wire, there's less resistance. If you have it flowing through a longer or a skinnier wire, there's more resistance. So in that way, it's sort of intuitive. Any other questions right now? Yep.
Are resistors like a physical thing that you change, or are they programmable?
Yeah, they're physical things you can change. So they're pretty little, so it's hard to see, but so like you can go over here and get a little resistor, and what that does is the part in the middle just for a given amount of voltage reduces the current based on the mathematical relationship that I'm going to talk about in a second. Okay, so yeah, for us, oh no, I have to look up. So they have little codes on them for what size it is, but
Not for those two.
what?
The system to like the ohms rating for each resistor is an app that makes it a lot easier to figure out.
Right. Yeah. Okay. Any other questions? One thing I want to say, and I'm just really going to say it like once, it can be a little confusing sometimes. So one thing I want you to notice with electricity is that current really comes from the movement of electrons. And electrons have negative charge. When we talk about current, so let's say the direction of conventional current is the direction of positive charge. So what we're going to call a positive current, or the direction of current, is actually going to be the opposite direction that electrons flow. Okay, that won't matter for our calculations, but if it ever pops into your head like, wait, how does moving negative charges make this all work? It's basically like the electron goes one way, and the mathematical effect of it is that conventional current goes the other way. Okay. So it goes opposite the direction of electron flow. So now the mathematical relationship between these things that I've brought up is called Ohm's law. And if you think of V as the voltage from one side of the device to the other, and you think of current, I, as the current through the device, and you think of R as the resistance of the device, then Ohm's law says the voltage is equal to the current times the resistance. Okay, so if you know the resistance of the device you're using, then this is the relationship between the voltage, like the pressure difference you apply, and the amount of electricity that's flowing through it. Okay, so let's do sort of as simple a calculation as you can do. Imagine you have a battery. Let's make this a 9-volt battery. And this is the positive terminal, and this is the negative terminal. And let's say with a wire, you connect it to a resistor. So this is like what that resistor looks like that I was holding up. It has little lines here that are coded to tell you what the resistance is. And then the other side of it goes over here to the negative. And let's say that this has a resistance of 1,000 ohms. If you think of a battery as having a difference in pressures on the two sides, the positive is the higher pressure. That's the higher electric potential. And so this battery, if you allow electricity to flow through a path, is going to try to push electricity out the positive side and towards the negative side. Okay, so electricity is going to flow from positive to negative. And we don't know what the electric potentials are of these, but we know that this side has 9 volts higher electric potential than this does. And if we want to know the current flow through this resistor, so what's the current through the resistor? Then we would use Ohm's law. And it says 9 volts is equal to IR, so 1,000 times I. And so I is equal to 9/1000ths or 0.009 amps, or 9 milliamps. Okay, and the direction of the flow is this way from the positive, this way through the resistor, and this way back to the negative terminal of the battery. For us to set these things up, we're gonna, have multiple resistors and multiple devices, and it would be kind of a pain. Like you see the wires over there against the wall. They have alligator clips on a lot of them, and we could set all this stuff up with alligator clips attached to batteries and then attached to one side of the resistor and whatever. But it's a little bit tedious to do that, and it gets very bulky if you have a complicated circuit. So what we're going to do instead of something like this is we're going to use these things called breadboards. And it's just an easy way to wire things together. Um, so it'll look something like this. And there on each side are going to be 2 rows of holes. Columns, I guess, not rows. So so there are these columns that go down this way, and then there are rows that go this way. And these holes are a size that you can just stick wires into. And the way it works is these holes are all connected. These holes are all connected. These 5 are connected. These 5 are connected. These 5 are connected. And actually I said 5, but on the ones on the columns, they're connected all the way down. Over here, there only these 5 are connected. But the idea is then, so let me show you what it would look like if we used a breadboard to create this same circuit. So we could use a breadboard to recreate the circuit from the example. So I'm just going to draw. I'm just going to draw the 5 holes that are connected on one of those 2 sides. But we could have the I need so if this is the battery, we could connect a wire and put one end there, okay? And then we could put our resistor across the gap here. And then we could send this one to the negative terminal of the battery. So that does the same thing as that picture I drew above. So let's think about how this works, okay? So current wants to go from the positive terminal of the battery around whatever circuit to get to the negative. And so current flows through here. Since this is on the same row of holes as this end of the resistor, the electricity that gets here also gets to here. Now it flows through the resistor because these 2 are not connected normally. So the only way electricity can flow from this row to this row is through the resistor. And now the electricity that's here is also connected to this, and it flows out of there. Okay, so breadboards are going to be something we're going to use all the time. And instead of drawing pictures of what we're doing with breadboards and batteries and wires and stuff, we're going to represent circuits with schematic symbols. And so a battery we're going to draw this way. There's a long end and a short end with like wires coming out of it. The long end is the positive terminal of the battery. The short end is the negative. A resistor we're going to show is like a jagged thing like that. A voltage source we're going to show as an open circle with a wire coming out of it, and it'll say like what the so we call it a voltage source. I mean, really, you could think of it as like an electric potential compared to the ground, but it'll say what its electric potential is compared to whatever ground you're using. So this is called a voltage source. And then this is the symbol for the ground. And you can think of the ground as having 0 electric potential. Okay, so the schematic for the example that we did would look like this. You have a battery down here, and it's connected to a resistor up here. This is 9 volts. This is 1,000 ohms. Okay, so when we're talking about circuits, just mathematically, we're going to draw this instead of trying to draw what the battery looks like and stuff like that. Okay. And this works exactly equivalently, by the way. To this, where I don't want that. So a voltage source of 9 volts connected to a resistor connected to the ground. Okay. In both cases, if you use Ohm's law, you have a voltage difference across the device of 9 volts. You have a resistance of 1,000 ohms on the resistor, and so all the calculations are the same. So you can use either one of these two forms. We're going to use this form a lot because when we start programming and wiring up our microcontroller for robotic stuff, we're going to have ports on the microcontroller that have a specified voltage amount source. we'll use batteries sometimes, but this is a format that we're going to see a lot. Okay, how are people feeling on this stuff? Anybody have any questions right now? So I want to bring up one more set of things. What happens when you use resistors together? And there's two different ways you can wire resistors together. So I want to talk about resistors in series and parallel. So series means electricity first goes through one device, then the other. So an example of this would be like if you have a battery and it's connected to a resistor, and then that resistor is connected to another resistor. Okay, so notice that there's no way for electricity to get to this second one without first going through the first one. Okay, so all electricity that flows through this circuit has to first go through one and then through the other one. When you have resistors in series like this, the voltage is divided between the two of them. So the way this would work is depending on what these resistances are. This one would be, if this is 9 volts, then maybe this would be 6 and this would be 3 volts. Okay, you divide up the voltage in between those two things. The current is the same through each resistor. And now if you think of the pair of resistors as a single resistor, like imagine, repackage this thing so that this is like a single resistor. So if you think of the pair of series resistors as its own single resistor, then the total resistance of the like packaged thing is equal to the sum of the two individual ones. Okay, so let me do an example of how we could use this. So let's say that we have a battery that's 5 volts and it's connected to a resistor there and a resistor there. Let's say that this one is 500 ohms and this one is 200 ohms. And say we want to know the current and voltage at each of those resistors. Okay. So what we're going to do is we're going to first lump these two things together. Treat this like it's a single resistor. And so I can redraw this schematic as it doesn't like when I do that resistor symbol. Okay, so we still have 5 volts here. This is the positive side and the negative side. What's the resistance of this combined thing? Yep, 700. And now this is a pretty easy calculation to get the voltage and the current. We know that there's a voltage of 5 here, like this. We know the current is going to flow this way. Ohm's law says that the voltage is equal to the current times the resistance. So the current is equal to, anyone have a calculator in front of you? I have a bag somewhere.
Yeah.
Okay, can you just, 5 divided by 700?
You want like a fraction or a decimal?
Decimal, I guess.
Yeah. 0.007 amps.
Okay. And we can think of that as 7 milliamps. Okay, so we know that there's 7 milliamps of current that's going through this combined thing. Now what can we, so now how can we figure out what's going on for the individual ones? Well, remember that for resistors in series like this, the currents are the same. So they're both equal to just 7 milliamps. I'll write it as 0.07. Okay, so now we can use Ohm's law again. So Ohm's law for the 500 says that the voltage is equal to the resistance of 500 ohms times the current. And so that is 3.5 volts. And now we can do the same thing for the 200. The voltage is equal to 200 times 0.007. And that is 1.4. That's round off error. They should add up to 5. Okay, so what we figured out is that there's 3.5, about 3.5 volts across the 500 ohm resistor and about 1.4 volts across the 200 ohm resistor. Any questions about that? Okay, last thing. So this was resistors in series. You also can have resistors in parallel. And in parallel, the electricity kind of has a choice. It can go through one or the other. So, like, for example, think about a battery. And it's connected to a resistor. There, and it's also connected to a resistor like this. Okay, so the electricity goes from the positive through here. When it gets here, it has a choice. It can either go through this resistor or this one. That's like fundamentally different than what we had with the series resistors, where there's no choice. You go through one, and then you have to go through the other one. Okay. And if you're doing this as a schematic, you can represent it like this. Some goes some way and some goes the other way, and that's what we're going to calculate is how much. So this time the current is divided, not the voltage. Okay, so so for parallel devices, the voltage is the same. Remember with series, we had the current was the same, the voltages are different. In this case, the voltages are the same, and the current is divided because just, there's so much electricity going through it, and some goes this way and some goes this way. That's dividing up the current. And so we're going to use kind of the same approach. This time, if you lump these parallel resistors together. So again, imagine that you package these two things into a single device. The effect is that 1 over the total resistance is equal to 1 over R1 plus 1 over R2. That's kind of the easiest way to remember it, but mathematically to calculate it, it works out like this. The combined resistance is equal to R1, R2 over R1 plus R2. That's just getting a common denominator, doing the math, and then taking the reciprocal. Okay, so last thing, let me do an example with a parallel resistor. So let's say that we have a voltage source over here of plus 5. And it goes through oh geez. Okay, and there's a ground. And let's say there's another resistor like this. And let's say this one is 100 ohms. And this one is 1,000 ohms. And we want to calculate the voltage and current for each resistor. Okay, so first I want you to notice, like, these don't exactly look, I mean, I didn't make them parallel to each other, mathematically parallel. But if you think about the definition of parallel, then you can tell this is the same as if I would have put it over here. The electricity goes this way, it gets to this branch, and then it has to decide some can go this way, some can go this way before it meets back up at the ground. Okay, so even though they're not parallel, those are in parallel. Okay, and so what I'm going to do is lump these two together. I'm going to treat this like a single resistor. And so R for the entire resistor circled in red is equal to 100 times 1,000 divided by 100 plus 1,000. And we get, can someone calculate that for me?
That'd be 90.9.
Okay.
Goes on.
Goes on and on. Okay. So this is ohms. And now we can use that to figure out what the, so we can, what are we going to do with this? Actually, we don't even have to do that, to be honest. We can figure out what the total current is. But since we know that the voltage for each one of these is the same, okay, so we know the voltage for each is 5 volts. Then we can go Ohm's law for the 100. Says 5 is equal to 100 times the current. So 5 100ths, so I is equal to 0.05 amps. And then for the 1,000, we know that the voltage is 5. The resistance is 1,000. And so the current here is 5 1,000ths or 0.005 amps. Okay. And if you add those two up, you'd get that the total current through both of them is 0.055 amps. And that's what you would get by using Ohm's law with that combined resistance. Okay. I'm going to give you some problems like this to try to work through this week. Feel free to contact me if you need help with it or whatever. And I'd be happy. I'm sort of assuming next week in class, we'll spend some time going through these because it takes a while to make sense out of this stuff, but we'll just slowly understand it. This is about as much complexity to resistive circuits as we're going to have to worry about. It won't really get any more complicated than this. Any questions? Okay, well, that's it for today. So the rest of the time we can just, I can answer any questions anybody has about the assignment that's due tonight. And yeah, that's it. Hi. There's going to be, we're still going to 3D print it.